So Scott Baker is a coastal engineer at National Research Council Canada based in Ottawa. Mr. Baker is a coastal engineer with nearly 15 years of experience in civil engineering hydraulics. He's a specialist in the application of physical and numerical modeling to investigate and develop solutions for a wide variety of problems in inland waterways and coastal regions. Scott has been responsible for numerous international modeling studies to help optimize and validate the engineering design of a long list of projects, including major ports and offshore platforms. And today, Scott will be discussing the research and development of a high-speed oil containment boom. And Scott, I see your slides. Looks like you're ready to go.
Thank you very much, Lindsay.
Thanks.
So yeah, just to move along. So the motivation for this work, there's really a pressing need for booms that are capable of containing oil at high speeds. So be that in fast flowing bodies of water, including rivers or areas with tidal impacts, or when you have high speed towing that's required to remove oil at a faster rate, for instance, in the event of a larger oil spill. So we know that conventional oil containment booms, they start to become ineffective in current speeds of 1 to 1.5 knots, or when they're towed at a similar speed. And certainly in some cases, their effectiveness can deteriorate in waves. So the objective here, obviously, to develop better booms that can speed up recovery, increase recovery efficiency, and try to reduce the impacts of spills. So the objective of this work was really to develop, assess, and validate alternative boom designs to increase oil containment effectiveness at high speeds. And in doing so, we wanted to demonstrate the feasibility of using CFD simulations, so numerical simulations, as well as scaled hydraulic model experiments to assess the relative performance of alternative boom systems. So in terms of the research plan, we first started with a literature review. So looking at oil, water, and boom interactions, specifically high-speed boom designs, and looking at what other authors have done in terms of numerical modeling and scaled experiments. And then we conducted our own CFD simulations, which I'll go into more detail, both 2D and 3D. And we also conducted a series of 1/8 scale experiments in our lab, again, both 2D and 3D, and we'll go into more detail on those. So CFD stands for Computational Fluid Dynamics Modeling. So for that, we use the OpenFOAM CFD Toolbox, which is a freely available CFD software. The main assumptions that were used for our modeling, we had a fixed boom shape and position. So we had a fixed boom with the oil and water flowing past that boom. And we had, in this case, just two-phase flow. So we had only oil and water as well as the boom itself. Both the oil and the water were assumed to be Newtonian fluids. And in this case, we've ignored any influence from air, wind, or waves in this particular set of simulations. We looked at 4 general boom types, so conventional, so with a single skirt, an L shape, a screened, and a ramped, and we'll describe those more in the next slides. Looking at flow speeds up to 5 knots, 3 oil types there given in the table, so a light, medium, and a heavy. And in total, we conducted about 80 simulations, numerical simulations. Some of those took several hours to complete, whereas some of them took several days to complete, just due to the size and complexity of the simulations. So in terms of the boom types, again, starting with a conventional single skirt, in this case, we use the DESMI row boom as our kind of target, just to start somewhere. So in this case, just a single skirt, we have the oil slick moving towards us from the right-hand side of the screen and interacting with the skirt. For an L shape, essentially using the same conventional single skirt, but then adding a horizontal, non-permeable L shape at the bottom there to try and contain the oil slick. Then moving on to a screen type boom. So again, in this case, using the DESMI speed sweep as our design basis. So in this case, we have 3 vertical permeable screens and then 1 horizontal permeable screen near the apex of the boom. And finally, a ramped boom. So in this case, we have a ramp That's the leading edge of the boom that's at a 15-degree down angle, causes the oil to actually submerge and then rise up behind that ramp area. And there are two kind of intermediate booms, which are non-permeable, as well as the main boom there at the far downstream end. So in this case, the main skirt, so item C there, is basically the same in all these different configurations, but different configurations up in front of it, essentially. So just to look at a few videos here. So this case, we have a conventional single skirt boom with a 3-knot speed with light oil. And we see, clearly the vast majority of this oil has just escaped. So we noticed that, of course, substantial oil loss occurred at speeds above, 1.5 knots. And it was even more difficult to contain the medium or heavy oils. And certainly through some analysis of deeper skirts, certainly they can improve performance, but there are of course practical limits for what the skirt depth can actually be. At some point, the forces on the boom and on the towing equipment would become substantial. So here we have the ramped boom system. So in this case, you can see the 15-degree down angle ramp at the far right side. So I'll just start the video here and we'll see our oil slick enter, and it gets again forced down by that ramp, but recirculates and resurfaces into this zone just above the ramp itself, and serving to effectively trap the vast majority of the oil into that kind of first compartment. We see a little bit of oil that gets deposited or brought up within the second and third components, and then a small amount of oil does escape, in this case at 3 knots with light oil. But certainly a significant improvement in terms of containment of light and medium oils at relatively high flow speeds. Moving on to some 3-dimensional simulations. So in this case, we're going to look at the screen boom system, again, based upon the DESME speed sweep. So we have a 45-meter U-shaped boom with 3 vertical screens and 1 horizontal screen. In terms of the numerical modeling, so in this case, the problem is basically a symmetric one. So we only modeled half of the boom to save on the computational effort. But even still, we had over 8 million cells within the computational mesh. And in this case, we modeled the effect of these screens by essentially blocking the flow through 20% of the cells. So here we have a short video showing at 3 knots with light oil. The left-hand pane there, we see the surface velocities. So you can see as the oil and the water is moving past these vertical screens, they do serve to slow down those surface velocities and allow the main skirt to capture a lot of the oil. And of course, on the right-hand side of the image there, we see side view and top view of the oil concentration. And in this case, we had very good containment of light oil at 3 knots. And again, a similar one looking at the ramped boom. So again, very similar type of results that we saw with the 2-dimensional simulations. And we see very good performance even with medium oil compared to the screen boom system. So moving along to our scaled experiments, again, first starting with a literature review. In that case, we determined that the best way to go forward with our scaled down experiments was to use what's called Froude scaling of the dynamics. So the actual tow speed or the flow speed of the water and the boom geometry. So both of those were scaled down according to 1/8 scale, according to the laws that you need to follow there. However, we didn't change anything to do with the fluid viscosity or the density. So we used, the normal water and oil for our experiments. In this case, we focused on 3 different boom styles, so the conventional, the screened, and the ramped, as well as looking at several variations of each of those. In our lab experiments, we used only 2 types of oils, so a light hydraulic oil and a medium gear oil. It was not possible to use a heavy oil in our facilities. In this case, we conducted 2D experiments with a fixed boom in a 2-meter wide by 97-meter long flume. So in this case, we had a flume where the water was able to effectively recirculate through the length of that flume. So we could have kind of a continuous flow of water as if you were in a river type of situation. And we conducted 48 tests without any waves in that case. For the 3D experiments, in this case, we had a 7 meter by 21 meter basin where the water was still. And in this case, we had a gantry crane which could actually tow flexible floating boom models through that basin. And in this case, we conducted about 43 tests, both with and without waves. And something important to note here, of course, with the numerical modeling, it's very easy to have the computer tell you exactly to the 10th decimal point what is the percentage of oil captured on upstream of that boom. But when you're conducting this many tests in the lab, it became very impractical to try to get precise measurements of exactly how much oil was retained on these booms. Therefore, we had to follow a more qualitative rating of performance based upon how much oil was seen to escape or pass underneath the boom. So looking at the 2D experimental setup, again, here you can see just the side walls of the flume. And we have one of my colleagues here pouring a pre-measured portion or volume of oil onto a ramp with an incline. And it would basically gently deposit the oil on the surface of the water, which was already moving due to this current generation system. And then a few meters down the flume, we see the oil interacting with the boom. In this case, at the lower portion of the image, the main white section there of the boom, that is the main skirt of the boom. And in this case, we have our model of the screen boom system. So we can see, at a few seconds later what it looks like. And then from another vantage point, again, a few seconds later, when all the oil has now traveled basically to the apex of the boom. And so you can see we have, in this facility, we have a nice vantage point from the side through the windows or from above to observe exactly what's happening in these experiments. So we have a few videos to show here. So this one is going to be our conventional boom with 1.4 knots of flow speed, again, a scaled version of that. And in this case, we have our light oil. And we'll just see here as the oil comes up and starts to interact with the boom. At some point, some of you with a keen eye, depending on the picture quality that's coming through, we'll start to see, certainly as we get a more larger mass of oil at the front of the boom, we'll start to see a few small globs passing underneath the boom. Start to see just a few, they're very small, but at 1.4 knots, at least with this boom design, it seemed that almost all of it was contained. But as soon as we go up to about 1.6, 1.5, 1.6 knots, we start to see more substantial oil loss. And certainly the medium oil, again, proved more difficult to contain. And these results were seen as very comparable to what was seen in the CFD simulations. Now we have the ramped boom, a video for that. So again, in this case, we have light oil and we've ramped the speed up quite considerably to a scaled version of 3.2 knots. The ramp itself is a clear sheet of plexiglass, so it's a little bit difficult to tell from the image, but we see it passing underneath the plexiglass now and resurfacing into that zone. And we see the vast majority of the oil coming up immediately into that area. And we can see smaller and smaller amounts of oil resurfacing into the second and third compartments there. And it's a little bit washed out with the light on the far right side, but we do see a small amount of oil has effectively escaped the boom and gone downstream. But again, the vast majority of the oil contained in this particular circumstance. Moving on to the 3D experiments. So just some photos here showing the different booms. So again, the conventional single skirt boom on the left there becomes the main component, the main part of our other booms. So effectively, we take that U shape and we just added or swapped out components in the middle. So adding some screens or the ramp and additional skirts. In terms of the experimental setup, so as I mentioned here, this is a picture showing our facility here. So again, a 21 meter by 7 meter long basin, and the blue gantry crane that we're standing on there would move towards the screen. You can see we have again a predisposed volume of oil that's being poured out onto a ramp, and just underneath the gantry crane we have our U-shaped boom that's being towed along, and we can see there the red oil that's been captured by the boom. And so just a couple of videos to show you here. Again, this is the ramped boom with a 3 knots, the equivalent of being towed at 3 knots speed. And again, we'll see very similar results from the 2D experiments, where the vast majority of the oil immediately resurfaces into this first compartment, and very, very little passing along to the further compartments. And one thing to note here, when we get to the end of the video, we'll reach the end of the travel for where we can go in the basin. So there is a fairly abrupt stop when the gantry reaches the far end. And one thing to note here, basically all the oil, even with this abrupt stop, almost all the oil is basically trapped within this compartment. So that does have a nice benefit for actually out in the field. If the towing vessels need to stop for whatever reason or change direction, the oil is pretty well contained within this compartment. We did notice that this ramped boom system the performance did deteriorate to some degree when you started to get into larger wave conditions, so certainly above 1 meter or 3 feet. So that was one observation. And here we have from a different vantage point. So we're looking down at the apex of the boom. So this is with the screen boom system. Again, a tow speed of equivalent of 2.5 knots with light oil. And we'll see again our oil passing into the apex here. And in this case, effectively no oil is passing beneath the apex of the boom, and very good containment at this speed. And our 3D experiment proved to be even a little bit better in terms of the percentage of capture compared to the 2D experiments. And this type of boom was only seen to have a very minor decrease in the performance when it was exposed to relatively harsh wave condition of about 3 feet. In conclusion, so for the CFD modeling itself, CFD techniques were shown to be very useful technique for simulating the interaction of oil and water with various oil containment booms and trying to assess their performance. As expected, the conventional booms performed pretty poorly at speeds greater than 1.5 knots. Certainly adding those vertical and horizontal screens to the conventional boom significantly increased the performance as we expected. And the ramped boom showed the best performance versus the screen boom when speeds were greater than 3 knots. In terms of the scaled experiments, so the scaled experiments were also shown to be very useful and a cost-effective means for studying this interaction of oil and water, trying to look at various oil containment booms, looking at their performance, and trying to develop modifications. In terms of the 2D experiments, they were ultimately easier to modify and test multiple designs. We had an infinite duration because of the recirculation system, and the windows really permitted a really good observation. The 3D experiments was maybe a little bit more difficult to get that close-up view, but they were ultimately more realistic because we actually had a floating, moving model. But our test duration was limited. We only had so long that we could conduct that tow. The screen boom and the ramp boom significantly outperformed the conventional boom, again, as expected. Both of those designs were able to capture significant quantities of the oil at speeds up to 3 knots. And the screen boom, again, was slightly better at performance in waves. So in terms of future work for the CFD modeling, there's certainly many other high-speed boom concepts that are out there. So we'd like to look at investigating more of those in the future. Also looking at 3-phase flow, so trying to include the air as well as the oil and water. So looking at, for instance, the effect of wind and how that might affect the situation. Trying to model the booms themselves as a dynamic floating body, so no longer being fixed. And also to look at the effect of waves with the CFD modeling. In terms of the scaled experiments, the scaled effects, there are some uncertainties in those. And certainly the best thing to do would be to repeat some of our testing at near or full scale to try to confirm those results. So certainly at a facility like OMSET to, again, try to confirm what we've seen at scale in the lab. And certainly we acknowledge that the tow durations in our 3D models were relatively short. So we'd like to repeat those with a longer tow to kind of confirm that time was not going to be an issue if we continued to tow at that same speed. And certainly the ramp boom design appears very promising and should really get further investigation to it. I'd like to acknowledge our partners here. So we had funding from the U.S. Bureau of Safety and Environmental Enforcement, and also partner with SL Ross. And I'm certainly happy to take any questions. And thank you very much for your attention today.
Fantastic. Thanks, Scott. That was a great presentation. And that's a really cool technology. Is there a plan to test that boom design in larger wave tanks anytime soon?
I guess we're working towards that. As I understand, Bessie is now maybe coming out with another round of funding, and NRC certainly plans to get involved with that. I would love to see us eventually get to OMSET. Our facilities are limited in size, and I'll be the first to acknowledge that the work that we typically do in our facilities aren't. This isn't the typical type of project for us. We do a lot more coastal, coastal structures and that kind of thing. So oil isn't our primary focus. However, it's something that's seen is certainly something that's important, and we'd like to see see that go further and kind of confirm the results that we've seen in the lab.
Great, thanks. And Jenna, are there questions from the audience?
We do have one question in the chat. From Greg McGowan. Could this system be deployed with a boom vane or equivalent for use in a high flow river?
So you'll have to excuse my ignorance here. So if you can explain what a boom vane would be.
It's
go ahead.
It's a device that you can deploy in a river, and it takes one end of the boom is attached to the shore, and it takes another end out across the river without a vessel. Mostly, I was just interested if the water was moving by, instead of dragging the boom quickly, would it have the same deployment if the water in a river?
Yeah, I mean, I think essentially the 2D experiments we conducted, it was essentially like modeling a river situation. So I think very much you could definitely rig something up that would be tied to the shore, but then be able to extend out into the main river channel and try to capture the oil there.
Great, thanks, Scott. And it doesn't look like there are any more questions. Jenna, are we all set?
All set.
Thanks, and thank you so much, Scott. Sorry if you felt rushed to try to catch up on time. I appreciate it.
No, that's good. Thanks.